When laser optics operate under intense laser irradiation, they might eventually suffer from damage. The damaged optical element doesn't work as expected and cause multiple troubles in various laser-based systems. In order to avoid unexpected laser damage, optical elements should be tested before use. There are several ways in which the lifetime of laser optics can be estimated. Let's call them classical and accelerated testing approaches. In this video, we will briefly overview how the classical approach works. To estimate, lifetime multiple S-on-1 tests are needed with different irradiation doses. Let's discuss how a single S-on-1 test is conducted. The sample surface is divided into a virtual matrix of sites. Each test site is visually inspected under a microscope prior to laser exposure. An inspected site is then exposed to a burst of maximum S laser pulses. Let's mark the laser exposure time on the x-axis. Each site is exposed to a fixed laser peak fluence, which can be adjusted by changing laser power. Power is usually monitored by the power meter. Let's mark different used fluence levels on the y-axis. A fixed number of test sites are exposed to a relatively short exposure dose. The fluence is increased for each site. When fluence is high enough, tested sites will be damaged. At short exposure doses, usually catastrophic damages are induced at high fluences. Then another set of sites is exposed with a longer exposure dose. The fluence is increased for each site in the same manner as before. However, as the exposure dose is longer, there is a possibility to induce non-catastrophic damage. For instance, the color changes. Following such an algorithm, the statistical data about laser damage is collected at various exposure doses. After the exposure, the sample is inspected under the microscope, and statuses of survived, non-catastrophic or catastrophic damage is confirmed for each tested site. During the real test, hundreds of test sites are exposed. Collected statuses and damage statistics are then used to calculate the damage threshold of every failure mode for the applied laser pulses, or exposure dose S. By having LITD data trend versus the time, it is possible to use extrapolation to make a prediction of the future. By applying advanced statistical methods, a prognosis of long-term behavior is made for each failure mode. Now, by having a prognosis of LIDT, a useful timeline can be estimated at the selected fluence level of interest. Optics lifetime estimation is particularly important for high-frequency laser systems, space optics characterizations, industry laser working at long-term exposures, and whenever you need to guarantee or make assumptions about long-time behavior. Contact Lidaris to learn more about optics lifetime testing and other ways to solve your laser damage problems.